In this very first lecture on quantum field theory, I will talk about the mathematical hardware that is required for relativistic quantum field theory. So, for a quantum field theory to be relativistic, it must be symmetric under the Poincare. I don't know how to pronounce that. I hope I'm pronouncing it correctly, but it must be symmetric under the Poincare group transformations. So to see what that means is consider a four vector that is x0 or x0, x1, x2, and x3, right? And consider that this four vector is the space-time coordinates in an inertial reference frame. Then in any other reference frame that an observer may choose, there is a expression or a relation that must be satisfied, and that is eta mu nu dx prime mu times dx prime nu is equal to eta rho sigma dx rho dx sigma, right? So this relation must be satisfied, right? Okay, so over here what we are doing is we're using the Minkowski metric, right? And that is eta mu nu which is equal to g mu nu, which is equal to 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 and 0 0 0 minus 1, right? Basically we have a positive 1 for the time part, and for the spatial part we have the metric as -1, right? And all the other spaces are 0. Now any transformation satisfying this equation over here in blue highlight, the relationship between the coordinates of two reference frames must be the linear transformation, and that linear transformation is actually denoted by a pair that is lambda and a. And now I'll talk about what is this lambda and a just in a bit, but this linear transformation must be of the form that is x prime mu is equal to this lambda mu nu. I don't recall, but I think I called this thing earlier gamma, but it's capital lambda, right? Okay, so lambda mu nu x nu plus a mu. Now some of you might from this expression over here that I just wrote figure out what this lambda and a is, right? But let me just go ahead and tell anyway that this lambda mu nu is a 4x4 transformation matrix, and it represents rotations, whereas this a mu is a constant 4 vector and it represents spatial translations. Okay, now note over here that the Lorentz transformation must satisfy a condition, right? And that condition, let me first write it down in index notation, is eta mu nu lambda mu rho lambda nu sigma is equal to eta rho sigma, right? And this is in index notation. Now, let me write it down in matrix notation, and it might seem familiar to some of you. And that is the Lorentz transformation must satisfy the condition eta transpose. Sorry, not eta transpose. It's actually lambda transpose eta lambda. So eta is sandwiched between the transpose of the lambda matrix and the lambda matrix, which is equal to eta. Now this condition, if you have watched my video on the general relativity, in the general relativity series, I made a video on symmetry and transformations, right? In that video, I have shown you where does this condition actually comes from, right? And this is the condition written in the matrix notation. Right. Now, these transformations that we have that are this lambda and A, they are the elements of the Poincare group. So they belong to the Poincare group that is P4. Now, we can quickly just check the group conditions, right, for the Poincare group. So the first one, the product, or you could say the composition, right, is say you have this lambda and A, and you take the composition with some other lambda, let's call it lambda bar, and some other A, the translation A bar, that is equal to lambda bar lambda and lambda bar A plus A bar, right? So that's the composition for this Poincare group. We have another one that is called the identity, and that is simply if you were to take this composition 1 and 0, right? So there is no translation and rotation is with identity, so that means there is no rotation. Take this composition with lambda and A, you are supposed to get back lambda and A, right? Now another one is inverse, and the inverse condition is that you have lambda inverse A inverse, the composition with lambda and A, that has to be equal to identity. So that's 1 0. Now the last condition is the associativity. I'm really bad with spellings, I guess. Yeah. So associativity, that is if you have this lambda A composition with some lambda bar A bar, and this is in brackets, and then you have composition with some another lambda, so let's call it lambda, sorry, not triple but double bar and A double bar. That is the same as if I were to do lambda A composition with this composition in bracket, that is lambda bar A bar composition lambda double bar A double bar. It kind of got congested, but I hope you can still see, or that's why I was repeating what I was writing. Right, now in index notation, the total effect of the product of two Poincare transformations is actually written as x prime mu is equal to lambda mu nu times x nu plus the translation, that is A mu, right? And x double prime mu would be written as some other lambda, so lambda bar mu rho x prime rho plus A bar, that is some other translation mu, right? Okay, so now let's actually talk about the quantum mechanical symmetries, right? So quantum mechanical symmetries. Well, these quantum mechanical symmetries are represented by unitary or anti-unitary linear operators as elements of a separable Hilbert space, right? So separable Hilbert space that is represented with H, and such that for each Poincare transformation that is lambda A, right, that belongs to the group P4, there exists a unitary transformation that is U lambda A is on H gives you the Hilbert space H, right? Now here, this identity unitary transformation and the product of any two unitary transformations of the elements of the Poincare group are physically indistinguishable from each other. And that is up to a phase factor that is exponential iota phi. And here phi belongs to the reals, right? So in the real field. Now, what I just said, I can write that down mathematically as unitary lambda bar A bar with unitary lambda and A, right? So this is the product of two unitary transformations, and they're physically indistinguishable from each other up to a phase factor that I just wrote, that is e to the power iota phi. So exponential iota phi, right? And phi is over here I would write lambda A and lambda bar A bar, right? And the product of this with the unitary transformation, now over here I would take the product of these, and so what I would get from, if I go back up here, I define the product property that is over here. So what I would get is from that lambda bar lambda and lambda bar A plus A bar, right? And so the unitary of identity, this one, is equal to exponential iota phi, and over here I would just have identity, right? Okay, so the family of transformations that is of this U lambda A, this unitary transformation that satisfies the equations that I just wrote over here, these ones, right? So one is this and the other one is this one. So yeah, again, the family of transformations that satisfy these equations is called projective unitary representation of P4, right? So the Poincare group. And it is precisely what we need to establish a quantum field theory that includes translations, rotations, and Lorentz boosts, right? These things as its transformations. So translation, rotation, and Lorentz boosts are the transformations. Now recall that rotations corresponds to the sines and cosines, while boosts corresponds to the hyperbolic sines and cosines, right? So okay, now let's do something. Let's actually consider the let me go down. Let's consider the time translation subgroup of the Poincare group, and that subgroup is this thing over here, where I have my lambda is equal to identity, And the I have time translation, right? So there is no spatial translation. We are considering specifically the time translation subgroup. And so therefore, A would be a 4 vector that would only have t, and the spatial coordinates would be 0. So this would belong to the reals, and it is a subgroup of P4, right? And over here, we are going to let U be a unitary representation of P4. And if we do that, then we have some V of T, which would be equal to U of identity and this time translation. So I would have T 0, 0, 0. This thing over here is a one parameter family of unitary transformations, right? Which is actually a group homomorphism, such that if we have this V of S and compose it with some V of T, that would be equal to V S plus T, right? So that's the group homomorphism. And this thing is then, it's called these things, this unitary transformation or the unitary representation is called a propagator in quantum field theory. And we will talk more about the propagator in quantum field theory in later lectures. This is also a solution to Schrodinger's equation, assuming that the Hamiltonian is self-adjoint, of course, and is stable, such that there are at most a finite number of, or even preferably 0 negative eigenvalues, right? And so the time-dependent differential equation is it's written as dv of t over dt is equal to iota h, where h is the Hamiltonian operator, vt, right? And so if you have a unitary representation, that is equivalent to solving the time-dependent Schrodinger equation, right? So you can see the power of that. And we require that these u lambda a is positive energy, right? So it has to be positive energy, right? What do I mean by that? That the spectrum of eigenvalues of the Hamiltonian operator is positive. So to write that down, there is a function that's called the spectrum or spec of the Hamiltonian operator belongs to the positive reals, right? And it has to be stable, of course. Now, let's say if this does not happen, if this thing is not a positive energy, then the system may be unstable and it would plunge to more and more and more and more negative eigenvalues, which is bad. Okay. Now, all the single particle unitary representations of P4 have actually been classified by Eugene Wigner. And actually, Eugene Wigner is the first physicist who recognized the importance of group theory in physics, by the way. Okay, so all these single particle unitary representations of P4, they're labeled by their mass m. And this mass m is actually invariant under Poincare and Lorentz transformations. And they're also, these representations are also labeled by what is called their helicity, or the spin S, right? However, even though that all of them are classified by Wigner, there is a bad news, and that is that the universe is comprised of many particles that creates tension between locality and interactions, right? So even for a single particle, as we increase locality, self interactions increases. So the particle interacts more and more with itself. And what happens is that new particles are then created via tunneling, right? So now with all of this, this was just a very basic first lecture on quantum field theory. Let's ask the question that why, even in the first place, obtaining a relativistic quantum field theory is hard. So, well, the reason for that is that constructing a relativistic quantum field theory is considered so difficult. It is because there are no non-trivial but only trivial finite dimensional unitary representations of the Poincare group P4. The only non-trivial representations of P4 are actually infinite dimensional, and therefore, of course, they are not easy to work with when we are constructing unitary representations. To understand this, actually, let's consider, in contrast to this, a more easily constructed group, that is the special orthogonal group of three-dimensional rotations, which is SO3. Now, this thing has a unitary representations that are u is equal to exponential iota sigma vector dot j vector. Now over here, sigma is the Pauli spin matrices, so it would have sigma x, sigma y, and sigma z, and j is your angular momentum, right? Jx, jy, and jz. Now, you might ask that why did I say that SO3 is more easily constructed? Well, the reason is the reason for that SO3 is easier to construct a unitary representation and work with is simply because SO3 is a compact group, right? So SO3 is compact. On the other hand, P4, the Poincare group, is actually non-compact, right? So I'm not going to dive into what is a compact and a non-compact group. Probably you know this, but let me just say this, that when I say a compact group, that is a group whose topology is compact, right? And compact groups have a well understood theory, right, in relation to representation theory and group actions, right? Okay, so yeah, this lecture is over. In the next lecture, we are going to talk about the classical field theory. I'm going to introduce classical field theory, and we're going to cover it very quickly because, of course, that would be a prerequisite to proceeding with quantum field theory. Over there, we are going to first talk about a field, and then we will talk about action principles and Euler-Lagrange equation of motions. And I will actually derive the Euler-Lagrange equation of motion, and we will look at some examples as well. For example, I might talk about the Klein-Gordon field in that lecture. So yeah, that's it.